The University of North Carolina at Chapel Hill is developing a telepresence video wall system for enabling informal conversations between remote coworkers. Image quality is an important requirement for seamless video conferencing applications. The UNC team has implemented an image segmentation algorithm that accounts for multiple overlapping foreground users during one-on-one conversations. In this project, 2 video walls have been constructed at UNC. Each video wall consists of 4 large-screen displays and a teleconference audio system. Eye contact is facilitated by switching between 2 sets of cameras as people approach the displays to speak with one another. Image segmentation is applied during this switching process to remove duplicate images that occur when a person or object is seen by more than one camera. The team's improved image segmentation algorithm responds to a problem that occurs when 2 people are having a one-on-one conversation in front of the display, and a third person walks past them in the back of the room. In this situation, traditional background subtraction algorithms are unable to distinguish between 2 people as they overlap one another. The person farthest from the camera is seen twice, resulting in duplication, once by the panoramic cameras and once in the foreground of the personal cameras. This duplication can be distracting during conversations. The problem can be addressed using stereo-based image segmentation. However, in practice, mismatched pixels result in erroneous depth values that can be equally distracting. The team's improved algorithm consists of 4 parts and successfully accounts for overlapping people through a combination of background subtraction and stereo-based image segmentation. First, a background subtraction model is created. Multiple background images are taken before people enter the room. Image noise is accounted for by modeling the color values at each pixel with a mixture of Gaussian distribution. Each pixel coordinate is described by an independent color distribution, and together these distributions serve as a background model for determining the probability that pixels belong to the foreground or background. This probability is then thresholded such that each pixel is assigned to either the foreground or the background. Next, images from 2 cameras are used to generate a stereo depth map. The binary foreground and background pixels from the previous step are used to create a mask that removes pixels in the background. In this example, 2 users are still considered part of the same foreground, even though they are overlapping. This problem is corrected by taking the histogram of all depth values in the foreground. Each pixel is binned based on its depth. Here you can see that pixels in the depth map share similar values at 2 different depths. Each depth pixel is then assigned to the closest overlapping foreground person by using an algorithm called non-maximum suppression. First, a window is slid across the histogram. The maximum value in the window is recorded at each step, and the peaks of the histogram are found by finding the intersection between these values and the original histogram. Finally, each depth pixel is assigned to the closest histogram peak, and each peak is said to represent a different overlapping person. The final step in this process is applying morphological operations. Having already defined segmentations for each overlapping foreground user, dilation and erode operations are applied to help fill in remaining holes and smooth out edges. The resulting image segmentation method successfully accounts for multiple overlapping people, enabling 2 people to maintain uninterrupted one-on-one conversations while people walk past them in the background. The team is currently working to integrate this method into the larger video wall and enhance the system even further by smoothing the transition between cluster and personal cameras using view morphing.